Cobot is one of the most frequently heard buzzwords of the automation industry. Likely you saw it in print or heard it in marketing speech. But it is also a word often misunderstood. Or one might even say that it is to some extent misleading. That is why the robot industry itself has stopped using the term cobot. Let's discuss the why and how. Hello and welcome to this excellent webinar on collaborative robot applications. This time we will cover the following topics. Why is the term cobot not used in the recent updates of the robot safety standards ISO 10218-1 and -2 and ANSI A3 R15.06? What are the key differences between standard industrial robots and robots meant to collaborate with humans? And what is a safe approach to human-robot collaboration? Likely you have seen live or in videos robots moving and performing diverse operations without any fencing or other safeguarding around them. People just walk by, work nearby, or interact with the robot, taking finished parts away or placing raw materials on a work desk for the robot to proceed. In particular, the number of robotic palletizing and packaging applications that run without apparent safeguards is growing. The robots used in such applications have special features. Most important of these are limited payload, low force, and low speed. Some may come with smooth or rounded or even padded surfaces, and some even feature so-called sensitive electronic skin that senses contact with the human body. The basic idea is to prevent injury upon contact between the robot and the human body. Such robots are often referred to as cobots, a term derived from collaboration and robot. The term cobot is mostly used to advertise robots that allegedly can operate without guard fencing and protective devices like light curtains, laser scanners, etc. Advertising videos show such robots operating almost anywhere. You can also see them on trade shows and fairs as they place products into crates and then stack them while onlookers stand right next to them. What is the impression you get? Wow, this is the next phase of factory and warehouse automation, only to be followed by Mr. Data and his Android colleagues. But what appears to be a smart concept at first glance, in reality is a misconception, at least to some extent. Robots that will always work safely around people in any kind of application simply do not exist. It is not the robot alone that counts. Cobot is thus a somewhat misleading term that makes people believe that they do not need to give much attention to safety when such a type of robot is used. Interestingly, the US and ISO standards for robot safety have never used the word cobot. And the terms collaborative operation and collaborative robot have been removed from the standard. Let's probe why. The new ISO 10218 standards published in 2025 and the US pendant ANSI A3 R15.06 use the term collaborative robot applications. This highlights that the application determines whether use of force and speed limited robots is safe or not. Fact is that the makeup of the robot itself is important for safety, but the application determines the risks and what types of safeguards are needed to deal with them. It is not the design of the robot alone that ensures safety. The new standards list numerous factors that must be considered to achieve a safe collaborative robot application. The objects handled, the type of end effector, that is, the tool or manipulator, any additional machinery and equipment used in the application, the mass, force and speed of the robot, the type of possible contact between robot and operator, the body parts affected, the space available, the surroundings and even traffic, and the number of operators, bystanders or walkers. Together, these factors result in a complexity that needs careful forethought, risk assessment. We'll come back to that a little later. Let's first look at force and speed reduced robots for collaborative applications. The new versions of ISO 10218-1 and ANSI A3 R15.06 differentiate two types of industrial robot. No, the differentiation is not between cobot and industrial robot, but between Class 1 and Class 2 industrial robots. Let's see. The difference between Class 1 and Class 2 industrial robots is in their manipulator weight, maximum force per manipulator, and their speed. See the values here. Manipulator mass of Class 1 robots is max 10 kilograms. The maximum force allowed is 50 Newton. The maximum speed at the relevant tool attachment point is 250 millimeters per second. You may be aware that 250 millimeters per second motion speed is the limit set for manual operation of industrial robots. This is roughly a quarter of normal walking speed and thus quite slow. The manipulator mass and force limits are new. These values are considered low enough to ensure that people will not normally be hurt upon contact with the moving robot. Consequently, the performance level requirement for safety functions of such robots has been reduced to PLR B or ZIL 1. Any robot exceeding these limits is a Class 2 robot. The standard PLR for robots in Class 2 is D or ZIL 2. Clearly then, Class 1 robots are meant for collaborative applications. But does this mean that simply selecting the right type of robot will automatically result in a safe application? Does it mean that you will never need to use guards or other protective devices? We have already considered some factors that determine safety of collaborative applications. When you think of the wide variety of tasks that can be handled by robots, additional risks likely come to mind. The end effector, the tool of the robot, may have sharp edges or pointed tips that can cut and pierce, pinch and nip points. They may also have hot parts, emit laser radiation, or apply and inject hazardous materials such as adhesives. Most of these risks can be controlled in some way. But there's an ingredient of collaborative robot applications that is much harder to predict and control: the behavior of operators and bystanders. The basic idea of a collaborative application is to have a machine and at least one operator share the same workspace. The type of collaboration may be sheer coexistence, but in most cases it will involve interaction. The machinery regulation, applicable as of 2027 in Europe, therefore requires the following: the prevention of risks of contact leading to hazardous situations and the psychological stress that may be caused by the interaction with the machinery shall be adapted to A. Human-machine coexistence in a shared space without direct collaboration, and B. Human-machine interaction. Interesting enough, the MR focuses not just on physical harm, but also on psychological effects of working closely around machinery that is potentially hazardous. Technology should not scare people or make them feel uneasy, tensed, or on the spot. Also note that the machinery regulation prompts manufacturers to consider not only the risks of interaction, but also those resulting from mere coexistence in the same workspace. Today already, a robot's next move may surprise an operator, and human reactions are often based on reflexes. Surprise or shock often causes jerky motion or a step in just the wrong direction. Also, people are sometimes distracted or may misjudge or misunderstand the operation and its safety limits. And last but not least, operators sometimes deliberately ignore or deviate from instructions. Their motivation rarely is ill-willed. It is the natural desire to be comfortable with the work situation, ease the strain, or achieve more that causes them to take shortcuts that may become risky. All these human factors may cause unwanted contact between robot and body parts. That may hurt or even cause injury. Therefore, note the 3 bottom-line safety rules for any collaborative robot application. 1. To protect people, do not rely solely on the robot's low weight, force and speed. 2. Try to prevent both deliberate and involuntary contact between a robot and operators to the extent possible. And 3. Avoid moving a robot at a height that brings grippers and other end-of-arm tools near the head or face of operators. These rules are set by the new ISO and ANSI robot safety standards. But how can we achieve safe operation? Risk assessment is the key. Do not begin by looking for hazards, like sharp edges and pinch points. This is an outdated approach and ironically may lead to overlooking the very hazards you want to detect. Instead, start by defining the tasks to be handled by the robot and the operator. Step 1. What are the work objects, the parts, goods, materials? Step 2. What end-of-arm tools will be needed on the robot? Step 3. Which stationary equipment will be needed nearby or on a desk? Will other machinery be involved, for instance, a conveyor, a lift, or a turning station? Step 4. What are the operations to be handled by the robot, and what do you want the operator to do? Will there or could there be several operators? Step 5. How much space is needed and how much is available? Step 6. Only now are you ready to look for the hazards. We already discussed many of them. For a moment, let us focus on 2 types of hazardous contact with the robot that the new standards explain and set limits for. ISO 10218 mentions 2 types of contact: quasi-static and transient contact. Quasi-static contact traps the operator between moving parts or between a moving and a stationary part. It may even prevent him from escaping. Squeezing, pinching, and drawing in are typical examples. The shape, the surface properties, and the force applied determine whether injury will result or not. A transient contact is temporary, usually short, and does not trap the person. Shoving, scratching, and cutting are typical examples. For these, the speed and impact energy are the decisive factors. And of course, the body part affected is crucial. There's a big difference between pressing on your finger with 50 newtons, the equivalent of 5 kilograms, or your face, earlobe, or eyeball. The revised robot safety standards therefore use a body model to assign limit values for both force and transferred impact energy to the different body regions. These are also differentiated by the types of contact discussed before. You will need to study Annex M carefully to come to the right conclusions regarding the severity of hazards from contact of robot and man. Once you have a clear picture of the type of hazard, you should carefully estimate the risk involved. Consider the severity of injury, the frequency and duration of exposure, the probability of the system or operator failing to work safely, the technical and human options for detection and avoidance of the hazard. Be sure to use a method that has all 4 risk elements and criteria with a reasonable resolution. We recommend the method presented in Annex A of EN IEC 62061, which is shown here. When the hazard situations, the hazardous events, and the risk are known, you can start creating a safeguarded space for operators and bystanders. The term safeguarded space has been used in robot safety standards from the beginning, but classically refers to a protected area that operators cannot enter while the hazard is present. That is, the robot would be fenced in and access points be monitored. For collaborative applications, these safeguards make little sense, but the new robot safety standards nonetheless use the term safeguarded space when outlining how to design a collaborative robot application. The aim is to create a space that is safe for the operator while he is there. That may even include barriers and fencing. The safeguarded space of a collaborative robot application should have clear boundaries. These may be marked on the floor, but could also be indicated by low so-called awareness barriers or impeding devices. Also, pedestrian guardrails and even fencing may be used. This will help keep bystanders and walkers outside the collaboration space, and as a side effect, it often improves efficiency of the operation. The revised robot safety standards present a systematic approach to the design of collaborative robot applications. They list 3 basic safety strategies and numerous safeguards that you may choose from. These are 1. Hand-guided control, 2. Speed and separation monitoring, and 3. Power and force limiting. Hand-guided control is a fairly old technique mainly used to teach robots. The 2025 standards introduce more stringent requirements and safety functions for hand guiding. Speed and separation monitoring relies on sensing equipment like laser range scanners and 3D camera systems to keep operator and robot from coming dangerously close to another. This is particularly valuable where a phase with operator interaction and a non-collaborative, more hazardous phase are planned in the same application. In such cases, the transition from high-risk operations without the operator present to tasks with operator interaction must be monitored carefully. Power and force limiting is based on the body model mentioned earlier. Where the results of a risk estimation indicate intolerable residual risk, one may add some measures, such as increasing the contact surface area, use of rounded edges and corners, smooth surfaces, padding, cushioning, deformable components, reducing or limiting of the speed of moving parts and forces or torques. Additional safety functions may also help. For instance, the time allotted for an operation may be monitored to ensure it goes well. If it takes too long, the robot stops. Presence sensing equipment can be used to determine the direction from which an operator may access the collaboration zone and at the same time communicate to the robot how fast a person is approaching. In some cases, your risk assessment may show that coexistence or collaboration of an operator with a robot in your application simply is not safe enough, despite all the efforts made. What then? Go for classic robot automation safety measures, like guards and control systems like light curtains, laser scanners, and contact-sensitive mats. Try to prevent contact between man and robot. Let me now summarize some of the takeaways from this webinar. Forget about cobots. Think applications. Do not think of a collaborative robot application as a limitless common workspace shared by a harmless robot and stuff you would love to save. As yet, there is no caring Mr. Data, neither stationary nor mobile. You may need serious safeguards, sensors, safety functions, and yes, even barriers and guards in some cases. Class 1 robots, service robots, and humanoid robots are not automatically or inherently safe, and likely they will not be for a while. A Class 1 robot may hurt your eye bad enough to cause a rush to hospital. An AMR with costly sensors may crush your foot while docking at a transfer station, and a humanoid robot with friendly LED smile may gently shove you downstairs. It's the task handled, the people, and the environment that decide on whether a robot application will be safe or not. Never cut corners when it comes to careful risk assessment. Yes, do your very best to create a safeguarded space that leaves people unhurt and makes them feel at ease at the same time. Stay safe with excellence.